AQA A-level physics. This is the electronics option, and this video is about MOSFETs. Now, what is a transistor? If you're doing this option, then on the core, you'll know very little about, you probably might not even know what a transistor is. You might not know about N-type, P-type semiconductors. I'm going to try and cover what you need to know without getting too heavily into it, because there's tons more that you need to know. Anyway, what is a transistor? What's a MOSFET? A metal oxide semiconducting field effect transistor is what it is. What happens inside a MOSFET? How does it work? You need a little bit of understanding of that. What does it do and what you can use it for? So, what is a transistor? A transistor is a bit like a valve which controls a current. Now, imagine a valve, and when the valve is closed, then there's no current. If you push a little bit, nothing happens. But if you push a little bit more, then you open the valve and lots of current flows. So a transistor is like a valve. Okay. Now, in a field effect transistor, this valve is controlled by a voltage. There's two main types of transistor. In the other type of transistor, it's controlled by a little current. A current at the base, we say, opens and closes the valve. Here, at the gate, it is controlled by a voltage. Okay? And basically, when the gate is closed, there is no current. When the gate is open, then a current flows from the drain to the source. That seems a little weird, but if you think about it, what's happening is that when a current is flowing, electrons are flowing from the source to the drain. Very strange, but anyway, we have the drain and the source, and the current is controlled by a gate. And if the gate is open, then current flows from the drain to the source. Okay, when the transistor is on, electrons flow from the source to the drain, current flows from the drain to the source. So MOSFETs do not require a current at the gate, just a voltage. And that makes them very efficient, and it makes them suitable for connecting to logic circuits. Hopefully you remember this graph here. Do you remember kind of EMF and internal resistance and stuff? And you should remember that the more current we draw from a power supply, the less voltage we get. So if you've got like a logic gate, like an AND gate or a NOT gate, if you start drawing current from that, taking current from it, then the voltage that you get will get smaller. And you don't want that to happen. So what you want is something with a very high input resistance. So it doesn't draw a current, so it doesn't change the voltage that you are looking at. So they have a very high input resistance, and that makes them suitable for connecting to logic circuits. Imagine a resistance which is controlled by a voltage. Now, looking at this diagram down here, this resistance here is controlled by this voltage here, VGS. Yes? Now, if this voltage VGS, which is between the gate and the source, is very small, if it's less than a threshold, yeah, below the threshold, nothing happens. If it's below the threshold, then the resistance is very big. So no current will flow. Looking at this potential divider, the bulb and the resistor, no current flows. So this VDS, which is the voltage across the resistor, voltage drain source, the drain source voltage is very big. So you're talking very, very big mega ohms. So no current will flow. So the transistor is off. Now, if the gate source voltage is above the threshold, then the transistor turns on. And what happens is that the resistance that we're talking about becomes very small, maybe 0.1 ohms. Yes, becomes very small. So the voltage between the drain and the source is also small. So all of the voltage is across this bulb in this case, and a large current flows, yes, down this potential divider circuit. So you've got this small voltage VGS, which is controlling a resistance, and the resistance is either very big if it's off, or it's very small if it's on. Looking at this, so when a voltage is applied to the gate, so there's the gate there, when a voltage is applied to the gate, what happens is that inside the MOSFET, you've got a capacitor, or rather you've got a capacitance. You've got two bits with a dielectric in between, yes? And what happens is this capacitor charges up and it creates an electric field, and that causes the MOSFET to conduct. That's why it's a field effect transistor. An electric field causes it to conduct. Okay? We say the capacitance charges up, so initially there's a little surge of current as the capacitor charges up. So we have this resistor here which protects the device. It protects the MOSFET so that little surge of current doesn't damage it. Then when we open the switch, we want this little capacitor to discharge, so we need another resistance here, yeah, between the gate and the source, and that enables the capacitor to discharge so that we can start over again. So you can turn it off, basically. If that wasn't there, then it would stay turned on, and you don't want that. There are some terms that we need to know. So VGS, that's the input voltage, if you like. It's the voltage between the gate and the source, VGS. Look at it, find it on the diagram. VTH, V threshold, that's the minimum gate source voltage required to turn the thing on. The gate source voltage is the threshold voltage to turn it on. VDS is the voltage between the drain and the source. VDSS is the maximum voltage between the drain and the source, which will be really equal to the supply voltage. And then IDS, when it's turned off, there is actually a tiny current flows through it, which we call a leakage current. It is very tiny. It's about 25 microamps, a very tiny little leakage current. Let's look inside a MOSFET, see how it works. We need to know a little bit about it. Now, I could do a whole long video about P-type and N-type semiconductors, but you're not going to get a question on it, so I'm just going to talk briefly about them if you don't know anything about them. There's two types of semiconductor. You've got P-type and you've got N-type. In an N-type semiconductor, you've got electrons are the charge carriers. That's why it's called N-type, because the charge carriers are negative. There's not very many of them. It's not like in copper wire. There's just a few negative charge carriers. In a P-type semiconductor, the charge carriers are called holes. Now, they behave like positive charge carriers, but what they actually are gaps where electrons can fit. So if you imagine these holes here, and as an electron jumps from one gap to another, so that's a negative charge moving there, yes, and that is the same as the hole moving, the gap moving from right to left. So you've got N-type charge carriers have a few extra electrons floating around which can move around, and P-type ones have a few extra holes in them which can carry electrons, and they behave like positive charge carriers. So you've got a metal body, piece of metal, metal base, yes. You've got a layer of P-type attached to it. Then we have 2 bits of N-type, yes. Then we have a layer of conducting material, no, insulating material, I beg your pardon, and that's my silicon dioxide layer. And that is an insulating material, and it also acts as a dielectric. This is my metal oxide, yes. Even though silicon is silicon a metal, it's actually a bit metally, yes. It's we call a metalloid in chemistry. But anyway, that is your metal oxide layer, the silicon dioxide, and that acts as the dielectric for the capacitor. And then we have another couple of conducting layers. Well, no, we have this conducting layer, which is for the gate, and then we have conducting layers which attach the source and the drain to the N-type. So our source is connected to a conducting material here, which is connected to the N-type, and the drain is connected to a conducting material, which is connected to the other N-type, and then the gate is connected to the conducting material here, and our capacitor, remember I mentioned a capacitor, is basically here. So we've got the 2 plates of the capacitor with a dielectric in between, and the dielectric is the silicon dioxide. Now, there's our capacitor. Just said that. Again, semiconductors are useful because we can control their conductivity. We control this by doing it by controlling the number of mobile charge carriers. And what you do is you dope them by adding bits of boron or phosphorus or whatever to make p-type, n-type semiconductors in silicon. Holes behave like positive charge carriers because they're basically gaps where electrons can fit. Now, between the N-type and the P-type, we get what we call a depletion layer. Now, the depletion layer is this orangey bit here. So this orangey bit here is the depletion layer, and that forms between the N-type and the P-type. What actually happens is that electrons diffuse into the P-type, and then holes diffuse into the N-type, and it behaves like a diode, so that current can only flow one way. A diode is actually just a piece of N-type and a piece of P-type joined together, a PN diode. You get this depletion layer which acts like a diode. One important point is that at the moment current can't flow from the drain to the source because the P-type is a very good insulator. Now, if we put a voltage between the drain and the source, by the way, we connect to the metal base, so that's earthed. If we put a voltage between the drain and the source, there is no current. There is no current because the P-type is a very good insulator, so there's no current between the drain and the source. However, if we put a little voltage between the source and the gate, so looking on this diagram here, if we put a little voltage, there's VGS, between the source and the gate, what happens is that our little capacitor charges up. Look, the top plate becomes positive, the bottom plate becomes negative. The top plate is the connection, yes, this layer connection between the gate and the semiconductor material. The other plate is the P-type material. And what happens is the top bit becomes positive, and any electrons which happen to be in the P-type material, there are some electrons that we call them minority charge carriers. Some electrons will drift up there, and so you'll get your positive, you'll get your negative, your little capacitor has charged up, yes, and we will get an electric field. There's an electric field. Now, if this voltage VGS is big enough, what happens is, now look at the orange bit at the moment. Now look at it. What's happened is that we have this conduction channel. Yeah, we have our orangey bit has extended, it's joined the two N types together. If VGS is big enough, then a conduction channel will form and you'll be able to get a current flowing. You'll get electrons flowing between the source and the drain. You'll get a current flowing between the drain and the source. And this happens when the voltage between the gate and the source is the threshold voltage. And if we increase the threshold voltage, then the conduction channel gets bigger and the current gets bigger. Is this all mega complicated and you're struggling to get your head around it? And the answer is probably yes. Okay, it's quite challenging. Do your best. It's the hardest part of the electronics option, I think, getting your head around this, MOSFETs. But there you go, tough. Looking at this graph, now this graph is VDS, your drain source voltage, against the current, yes, IDS, the current flowing through the transistor. Now, if VGS, the gate source voltage, is less than the threshold, as I said, there's a tiny current will flow, 25 microamps, tiny, ignore it, it's not really important. This leakage current is called IDSS, okay? And this is called the cutoff region. Basically, the transistor is turned off, and on the graph, it's the cutoff region, which is this. It shouldn't even be on the graph because it's such a tiny current, but it's this area here where the transistor's turned off. Nothing's happening. Now, if we make VGS bigger, then this conduction channel forms. VGS is greater than the threshold, and basically we start getting a current flowing. We've got this bit here called the ohmic region, and basically the output voltage is proportional to the current flowing through the transistor. That's called the ohmic region because the graph is a straight line going up. There's a limit to how much current can flow because the conduction channel is only so big. There's only a certain amount of current can flow through it. So at a certain point it becomes saturated, and this is our saturation region here. How do we make the conduction region bigger? Well, what we do is we make VGS bigger. And if we make VGS bigger, then the conduction channel gets bigger, so more current can flow. So we have our ohmic region. So our ohmic region, our saturation region, and our cutoff region. Now, really, all we need to worry about is the fact that the transistor is either off, which is the cutoff region, or it's on and it is saturated. Yes, because we're only worried about this transistor as a switch. It's either on or off. So it's either the cutoff region or the saturation region. We're not bothered about the ohmic region. That's where you would use it as an amplifier. And we're not going to worry about MOSFETs as amplifiers. They're either on or they are off. And when it is turned on, if you need any data, if you want to know what VGS is, if you want to know what VDS is, or what the current is, you'll be given this graph and you'll be looking at the saturation region on the graph to get your data, not on the ohmic region, he says. So all we need to know about is using the MOSFET as a switch for connecting to logic circuit. Okay, so using a MOSFET as a switch, and here's a simple circuit. R in, we know why that's there. That's to protect the device as our little capacitance charges up. RGS, we know why that's there, so it can discharge, so it can turn off. And if V in is low, then VGS is below the threshold, So the resistance between the drain and the source is very high. The bulb will be off. There'll be no voltage across the bulb. It'll all be across, it'll be V out. It'll all be across the drain and the source. If V in is high, so RGS is above the threshold, then RDS, the resistance, is going to be small, about 0.1 ohms. So the voltage will be across the bulb, not across the VDS, and the bulb will turn on. Okay, so you've got off and on. If you get a question, then basically it'll either be, the transistor will either be off, which is on the cutoff region, or will be somewhere in the saturation region. And looking at that, you can take the value of the current, you can take the value of VGS, you can take the value of VDS. So you'll be given this graph. So we've covered an awful lot in this video. It's quite a long video. Here are the key points. MOSFETs have a very high input resistance. That's because of the silicon dioxide layer. Yeah, it's a very good insulator. This makes them suitable for connecting to logic gates. An important use of MOSFETs is as a switch, connecting logic circuits to power circuits, for example, turning a motor on and off or turning a bulb on and off. The output current is controlled by a voltage, not a current, as in other types of transistor. The MOSFET conducts when the VGS is above a certain threshold voltage. Understand a little bit about why in terms of what's going on inside. RDS, the resistance between the drain and the source, goes from a very high to a very low resistance when it turns on. So the voltage drain source goes from a very high value to a very low value. Rin protects the MOSFET from this charging current when the field is created, and RGS allows the capacitance to discharge when the input voltage falls to zero. Thanks for watching. Hope you understood that. Let me know what you think of the video.